Hey, hi everyone. Today we have Yaorong presenting contrastive learning inverts data generative process.
Hi guys, this is Yaorong. This is paper contrastive learning inverts data generating precise. I will presenting it today, and which is published by this guy from German. And my presentation will just cover three parts, and I will give a brief background of contrastive learning and one of the most popular contrastive laws, the influence laws. I will briefly go through that because there are all of the basic definitions will be used in this paper. And I will spend most of the time on the theory part. There are very mathematical and a lot of formulas there. And then give experiments on how they prove and how their theory applied in real data. And the three main contributions from this paper is just like the title, to mention as inference, which they use as to prove this paper. The contrastive learning can invert the data generating precise. And based on some statistical assumption, they will have a couple of different assumptions to prove this precise. And also they prove that also there's some assumptions are validated, they still can be achieved. And they give the experiments results on the to approve that. And the last one is for their result for our real image data. And we will cover all of this in later. So I will quickly go through contrastive learning in just one page. So if you have never heard about contrastive learning, it is a self-supervised learning technique. Basically, the intuition from contrastive learning is to make similar data in the latent space be closer enough, and the dissimilar data to separate as much as possible. So what this contrastive learning do is trying to train an encoder which embed image or data, whatever you have, to a latent space, and you have augmented positive images, which we compare it as positive, which means they're similar, or other what kind of you define positive images, and make them similar in the latent space. And this similar from a negative samples, like from this example, you put a tiger to monkey. It's we consider it to be a negative and make them far away in the latent space. So this is the basic, just the basic intuition of contrastive learning, just for the idea of it. And then we need to know about the formula of influence. Maybe for this paper, it is not important that you understand why they got this formula, but you just need to know they will try to prove everything based on this formula. Is the influence from the paper representational learning of contrastive learning. I forgot the name there, but it's that paper very popular. And the basic idea of this function is trying to maximize mutual information between the context and the prediction, which is like you have the input and output, maximize mutual information, similar idea compared with the Infomax. And this is a representation of mutual information, and they are trying to simulate similar measurements or of the two latent data to be proportional to this part of the mutual information. And finally, they will prove that by optimize this loss function will maximize the lower bound of the mutual information. So based on this background, let's start with this paper. So what they're trying to do is on the abstract, they mentioned that contrastive learning can learn powerful features from given data. And there's always question that why these learned features are so powerful at downstream tasks. So what they're trying to do is prove that it's just a basic generative inverse of generative part. So this is why it's very efficient, and they proved everything there. And before going to the theorems of them, they make some assumptions to prove and this is one of the three figures in the paper.
One of the only three figures.
Yes, and they assume that Z, which is coming from the unobservable space, which is something we don't know. For the sum based on all the images, it's generated from some latent space, but we don't know about that with the generator. The generator and the space are unobservable, but they assume that this latent space is a unit hypersphere, and the ground truth marginal distribution of the lattice is uniform, and it is a Van Mises Fisher distribution. What is this distribution is? Basically, this distribution is just some kind of distributions on a hypersphere, and its formula is defined. There is a CP minus 1, blah, blah, blah. And the C represents the normalization constant, and the K represents concentration parameter, which, like, if you consider this is a Van Mises Fisher distribution, this will be the concentration point. The higher the K is, the more density of points will be near the concentration. The lower, the higher will be on the concentration point. So this is basically their assumption, and also this is assumption of they assume that the ground truth latent space is uniform distribution, which represent like this. This is some basic assumptions they made, and based on this, they're going to prove this following three ideas. First, they will try to prove that the contrastive learning by optimizing the info NCE, which they will use, is similar to minimize the cross entropy. And also they prove that this process also identified the ground truth factors on the hypersphere, which is conditional ground distribution. And then they will make the ideas more generalized to a convex body, not only on the hypersphere, but to a more convex body like a hyperrectangle or even unbounded distributions. So, well, now this will starting with the annoying part. For the theorem one, basically, well, I will go through maybe line by line through the theorems. I just trying to make things more simple and clear. So what they're trying to do, the theorem one they gave is the max optimize the influence function, which is this one, the right corner one, and it's basically the minimization of the cross entropy between this P is represent the ground truth conditional distribution. And the QH, which is parametered by our training encoder. So this process will minimize the cross entropy between this distribution. So how to prove that? And given because we already assume that the conditional distribution, which is assumed to be a Van Mises Fisher distribution, we already got this formula. C is constant, and here is with there, just to put this part into the cross entropy function. While a lot of parts, many formulas from their improvement process, it's just expand cross entropy formula there, and you will get this result. And because they have assumed that on the ground truth is uniform distribution, but open the brackets, putting that you will get this result. I will not go through the improvement part, but I think it's
so let's go a little slower though. Mm-hmm. What is M? Number of samples, right?
M is number of negative samples.
Negative samples. And Z is the size of the space, or
the size of the latent space.
The latent space. The dimension.
Number of data.
Inverted dimension, maybe.
Well, M is number of data. Why do we need the plus log z, what does that encode? I'm trying to see. It's d-dimensional space, right?
Yes, in the lens. Yes.
Yes, so like when they say P of Z equals inverse of, so it's 1 over D basically. Number of dimensions, 1 over number of dimensions.
Yeah,
Each dimension is equally likely.
Yeah.
It's the marginal is uniform. Okay. And the limit m goes to infinity, that first part. Not can you go back? Here, the top part, it's the objective function that they're optimizing, right?
Yes. The
And
objective function is just these are constants.
yeah, okay. They're constants, but why? So von Mises-Fisher is a unimodal distribution. So they're only talking about one factor, right, at a time. Each factor is a von Mises-Fisher distribution. It's a mixture of factors together, or
What do you mean factor?
like a latent factor, what is represented there. So they're doing like clustering, or well, they're not doing clustering, but they're claiming one of the factors, one of the directions is preferable or it's unimodal. Why would be the latent space unimodal? I don't understand. Von Mises-Fisher is a kind of unimodal distribution. This one confuses me. So do you need to prove for one and then just scale? Okay, we have multiple modes, or each one is just unimodal von Mises-Fisher. Do they talk about that at all?
No.
It feels like
I didn't go deeper in of that distribution thing.
No, but look at the figure, the one and only, right? This is unimodal. There is only one mode on the hypersphere. But well, if you look at von Mises-Fisher formulation, you see that it's falling off exponentially. It's like a Gaussian, but on a sphere, basically. So why a single Gaussian? I don't understand. Okay, but let's go on. I was just trying to clarify some details. Yeah, so the first arrow is clear. You're just using the definition of cross entropy. That's how you got the negative sign and all. But then what happens next?
From
22, 23, 24. What is there? So at first you're using linearity of
Z is the uniform.
so your log over the integral. No, I don't understand where you exactly use the property that it's uniform. You turn integral into expectation. Okay.
The explanation of log Z. Why is this? You mean from 23 to 24?
Yeah, even from the one above to 22, 23, 24 to that new block. The only change is the integral becomes an expectation, right?
Oh.
No, I'm trying to understand what they're doing. What has changed? What are they doing?
No, there are something else there. But the improvement maybe is based on another paper. There will be another 3 pages of formulas to prove everything.
Yeah, that's fine. But if I miss transition right now, then I will not follow.
Well, it's suggest the precise of this function.
Okay, let's continue. That's fine. I'll ask questions again, and I will think about it.
Yeah. So, I think it's then we get this part. And so based on the information here, and the paper used another proposition from this paper. I didn't go through the details of that. So they just the paper just mentioned that and they use their results and applying to this part. So H is represent the F, G is the generator, and F is the encoder we're trying to train. So H can be written to that, and by putting this function, all of these two parts are forming this paper, and they can get this result. And finally, prove that it will convert, and it will get in this result, which is to prove that by training the influence function, it will convert to cross entropy. Okay, I guess this may be not clear, but this is how they prove that. And so based on the theorem, so the next part, they're trying to prove that the minimizers, which is next in the optimization of which is the cross entropy will maintain the dot production on both the Latin space and the reconstructed Latin space. So what they have done, if we can have an optimizer based on the before, like we have optimized across entropy, we will have the ground truth condition distribution equal to our parameterized conditional distribution. So because it follows von Mises Fisher distribution, so we will put this values into that and prove that, because they still based on another something like that. They will let H represent the mapping from onto a hypersevere with a radius of square root of r at tau k. Tau is the temperature value of the influence. And so then you can prove that, get the result, this part on this part equal, and we'll get the normalization constant equal. And then you will get this part are equal, and prove that you can have the dot production is just a constant scaling between these two spaces. I don't know if is everything clear, because I'm just trying to transfer the information from their proposition part.
Yeah, so what is the proposition in simple words then?
It's just didn't highlight it, but it's just for any Z and Z, they will constant value to maintain the dot production. Z is the ground truth constant Latin space, and HD is our reconstructed Latin space.
And they're normalized.
Yes.
So it's a cosine distance basically between this. It's a scaled cosine distance. That's what they're trying to say. Z transpose Z tilde transpose times Z tilde. If they are normalized, it's just the angle between them, right?
Yes.
I guess they're trying to group together the positive and the negative samples. And like they're trying to repel all the negative samples from whatever the positive.
Oh no, what the objective is doing, I know, but what is like the objective is doing some kind of a metric learning. But
I don't think that it's cosine similarity. I mean, you are anyway you're working with the hypersphere here. I'm not sure if that would.
Yeah, it is cosine similarity. Inner product on the hypersphere, right? But
what they're trying to do, they're trying to prove the asymmetry of the two space, so that they can get like a 1 by 1. So since they are proving with this, it's just a scaling change and the dot production relation.
So H is any function?
No, H is just okay, you should move your
You can determine.
always
You can press the minus button.
Not put that. It's H is just the, I will. The whole process from the left to the right is H. There will be a generator and an encoder. There's our observation space. The whole process is H.
Yeah, but H produces Z, right?
They don't. No, yes. No, it's H produces Z, the reconstructed Z.
Oh, reconstructed, but it produces X then.
Yeah,
Like
H
the data, right?
transport times is the delta is in the reconstructed line space. And the Z transport time is in the unobservable line space.
Oh, okay. It's in latent space
Oh,
and this is a reconstructed space. Okay. So what they're claiming is that reconstruction is inner product in the reconstructed space is just a scaled inner
Yes.
product in the latent space.
Yeah.
Okay.
How are you scaling it in the reconstructed latent space?
How you get this?
Yeah.
They have still they assume that H maps to the hypersphere with radius. This one.
Right.
Maximus, right? R and tau K squared, and because based on theorem 1, they have proved that is like a cross entropy. So finally, if you get a minimizer, you will have these two distributions the same.
But so cross entropy in this case, I'm thinking if we can relate it, or if we can map it to like clear divergence. If you're basically trying to check if two distribution in this is similar or not. That's what contrastive learning does in general. Whenever you're trying to find the positive and the negative sample as well. So assuming that that's what they are also saying, how do you reconstruct it in the latent space? Like how do you what exactly is happening in the problem?
Z is the latent space and they're trying to invert it with H, right? Is Z the input
Yes.
or the latent space? The latent space.
Z is
Z is the latent space and Z tilde is the reconstructed latent space. Right?
No, I don't know what Z tilde is.
This is the positive samples.
Yeah,
And
it's all in the latent space. So basically what it says in the next proposition is that inner product in the reconstructed space is just a scaled version of inner product in the latent space. The angles are preserved up to like the scaling is changed. So the scaling would be changed, I guess, if the sphere has a different radius.
Yeah.
So it's just everything else is preserved, it's just the radius changes. Right?
Yes, this triangle will be triangle.
No, I'm looking at the last line of this proposition 1 block, not the footnote, but
Which one?
yeah. K Z transpose Z tilde equals H Z transpose times H Z tilde, right?
Mm-hmm.
This one. So that is claiming
Yes.
that it projects onto a different sphere, so it changes the radii or something.
And also in the bracket, they mention minimizer is also cross entropy maintain the dot product. This is the proposition.
Yeah, so maintain the dot product is they maintain the angles.
Yes, they will try to prove step by step. And then they will have the proposition 2, which is based on the theorem 1 and proposition 1. So because we already, based on proposition 1, they have proved the dot product intent. So in this condition, they have 2 provement with radius is 1, the radius larger than 0. And so I'm given the provement for the R equals to 1 there. So for this condition, for any Z belongs to the latent space, we'll get this equals to that. and with the derivative of based on z and z delta, and they will get the Jacobian function is orthogonal.
So they're assuming H leads to the minimum scale divergence, right?
Yes.
So H is that function that provides us minimal scale divergence. Then this inner product thing holds.
Yeah.
So okay, for a trained network or whatever, for a function that minimizes scale divergence, the inner product rule holds. That's better. Can you start with 38? What happens there?
38.
Equation 38. So
What's the derivative of this part based on z? We'll get the Jacobian function of it. And the left side is derivative will get z delta. And then based on 38, they will partial derivative on z delta, and they will get identity. And the left side will get this two Jacobian matrix. So we can get Jacobian matrix is orthogonal. And so they prove that this HC is an orthogonal linear transformation. Things so clear, right?
But if in a matrix, let's say matrix multiplication normal, if you do dot product and the product is one, then isn't it again the orthogonal linear transformation of that? I'm not able to understand like what they are proving exactly. Are they saying that this also implies if your dimension is, let's say, if you're in a higher dimension because you're working with hypersphere?
no, I think they're kind of establishing some simple stuff here for us to follow the theorems later. Like, first, they're saying scale divergence, any minimizer of scale divergence, any function that you plug in and gives you zero scale divergence, leads to preservation of inner products, 37. Input inner product in the input equals the scaled version of inner product in the output of that function. That's one. From that, immediately follows that the Jacobian of that function is orthogonal, is invertible. Yeah. This is kind of elementary once you agree with the first fact. That's they show this instead. But why they're doing that, I don't know.
Oh, at least mentioned is that trying to prove this invertible. So because I may mismatch some part of it. I like a lot of theories there. I'm just trying. If I didn't guess you, it's trying to prove it's invertible because it's trying to given the inverse of the generating person.
So just connect all of that together is that they're saying a minimizer of scale divergence has an invertible Jacobian. That's my reading.
Yes, and they will summarize everything in like this theorem too. This is just basically following all the steps about it will return Latin source after orthogonal transformation and with a constant scaling factor when all of the above assumptions are conditioned.
And this is true only if the latent conditional distributions are from Mrs. Feature.
No, so
And
then they will make it more generalized to like a hyper rectangle. But also in their experiment, when it's not only a hyper rectangle like in unbounded space, they will sometimes have achieved a better result. Not better, a good, relative good result. Is it just trying to prove one step by step? The question you ask may be something related to the future steps of it.
What are the properties of f and g? So you have composition of two functions, f and g, right?
G is unknown. You don't know G.
So there
This
is
is also based, their assumption is based on, you know, the unobserved space, but in real life, you don't know.
okay. So there is some mixing, nonlinear mixing process that takes in on Mrs. Fisher distributed latent factors and produces the observations that were there, right? Or and the cruise ship. And then we are trying to reconstruct that latent process, and we can reconstruct it up to a scaling factor because inner product will be the same, or rotation as well, because we can preserve inner product by rotating everything totally off, right? The inner product will be preserved, but rotation could be arbitrary and still inner product.
Yes, they mentioned that like in their one of their experiments on when the normal distribution, the rotation problem they cannot solve.
Yeah, this is ambiguous. Like any rotation will work. Like rotation preserves inner product as well. So
yes,
all angles.
Yeah.
Okay. So f is the reconstruction function. So putting it back to the ICA language, right?
Yeah.
So f reconstructs from the mixtures is trying to reconstruct sources. G is the mixing function from the Z.
Yes, G is yes.
Yes. Okay. So this theorem, I'm trying to like figure out just this. Can you summarize this theorem in your own words?
Yes,
you're doing well. But
I'm reading this right. The four readings.
Yeah. Go ahead. Can you summarize it in your own words?
What?
Can you summarize this theorem in your own words, just to help us? Otherwise,
I think
feel.
this is already summarized. Because
Okay, let's ask Rinaldo to summarize it.
They have a lot of assumptions. They have a lot of. This is why I just pasted it there. I tried to summarize things, but
In terms of ICA, everyone here worked at some point with ICA, and we know kind of how it works. Can you summarize this theorem in terms of ICA? What does it mean? What does it mean?
Okay, I think it's better for using it. So like in real life, we can have like we have observation in this part, in the middle part, which is it could be like for ICA problem, it can be a mixer part. We don't know about the generalization things, but we are trying to train a model to get this one to have this separate doors from so-called latent space. And based on the assumption there, they assumed that all this reconstructed latents or our separated sources followed von Mises Fisher distribution. And based on their theorem, like they can minimize the cross entropy between the conditional distribution, ground truth conditional distribution, and our trained distribution. So we can assume that this precise. And also in the proposition 1, they're trying to prove that in the two spaces, it will fall in the latence, the dot production just as scale with a constant scale. So this process is can be treated as an invert of this generating process. I don't know how I mean, it makes it even more confusing. But it's just like if I say problem, this is the force on our mixer, and this will be the separated force.
Yeah. I don't know what we're gaining though, because this rotation problem still has to be solved, and it's difficult. Like we're not getting sources still, right? Because everything is rotated. And then multidimensional space C, it's like how do you know where are the true sources? So they kind of like
It didn't give me
mixed.
What?
They kind of like, they're still mixed, or when you rotate, it's still kind of a mixture, right?
Why? I don't think so.
Okay, well, let's see how the experiments look like, or how the next theorem, what they're trying to prove looks like.
Well, for them the support is like everything about we have proved on more like a convex way, like a hyperrectangle. So their proof steps is just exactly the same, just the proven process is even more complex. I didn't paste everything there, just the change is that they changed the dot production there with the delta, not delta functions, something of the norm. I didn't give through of the details of the delta function.
Are they trying to be general, that it's not just a product, but any similarity? Those
Yeah,
products
they're
will
trying to-
cosine
The
similarity.
other there is trying to do norm. We need to found. Okay. There's too much.
So it's delta contrastive instead of the original kind of inner product definition.
Yes. For me, I just because I didn't go that deep of this formulas. The delta is which dimension is like to similarity measure or symmetric between the.
Well, I'm just looking at their capital L, calligraphic L.
Oh, this is
Delta contrastive definition, right? They changed.
Yeah, they just changed it.
Okay. Why? Oh, okay.
Because they will make it more general. So you ask her why, I didn't go through about their proof, I just paste everything there. So the theorem and proposition is all the same. The theorem one is just our theorem, the theorem 3 is just the theorem 1, still trying to prove the cross entropy thing, but it's based on the delta function, based on the delta. And the proposition 4 is also trying to prove the asymmetry between the latent space and the reconstructed space. But so with lambda and the tau, lambda is a hyperparameter in the delta function. I didn't go through trying to paste everything of this part in there because there would be more functions. And still, so as my plan, I was trying to quickly skip this part because this.
Wait, can you go back theorem 4?
Theorem 4.
Yeah. But what I'm able to understand is like they have, they have some distribution which is like a hypersphere or some geometry, in this case, rectangle or something. And it's like this. You have like a cloud of all the samples, including positive and negative samples, and your task is basically to invert it or change the direction of each and every sample so that everything comes, like all the positive samples are basically at one place and all the negative samples are at some other place. Like they're all opposite to each other over it. And that is what they're trying to do here as well. So like when you have this CQ, which is of Z, you're integrating over all the exponential of everything. So it means like you're not just taking like one sample, but you're basically taking integration over all the each and every sample of that hypersphere, and then you are trying to for the Q of H, which is Z delta, given that you already have the Z, you are basically trying to check if all the samples, like what is the similarity between each.
It's just a normalization factor.
Exactly. But that's what they're doing. That's what I'm trying to do. That's exactly what they're doing. But it seems like pretty complicated in this case.
No, what they're saying is any, like H is non-linear, right? As long as, again, coming back to theorem one, as long as H is a minimizer of the scale divergence, defined by contrastive, the incoherency objective. Theorem 5 at least says that we can recover it up to a fine transform. But recovering up to a fine transform means we have a mixture. We still need to run linear ICA now. Do they run another ICA on top, linear ICA, to recover that fine transform?
Any experimental ICA. They just mention something related to ICA, then.
Well, then there should be another theorem, right?
Yes, yes.
Like the fine transform is not helpful, it's still linearly mixed. At least that's what I'm seeing. Yeah.
Hey, I have a question. Maybe I missed the beginning. Did they assume independence in the latent space to begin with?
Yeah, do they assume independence of Z's in the latent space?
Before the generation.
No, I don't think so. It just mentions they're uniform distributed.
Marginal is uniformly distributed, but they assume unimodality. That's kind of
This is
strange.
not a mention uniform.
So maybe this is not about independence.
Oh, yes, they didn't mention them.
This is about in identifiability, right? Reconstruction.
Yes. It's more about it in final.
So in your figure, what Rogers is asking, in your figure on the left, in the first
Yeah,
figure with the,
they didn't mention independent.
yeah, anything about.
I don't think they assume it's independent. So maybe.
So you would be warranted running ICA only if independence made sense for your particular data set. This is maybe more
Yeah, but
general.
then I don't understand what they recover at all with affine transformation. Residual affine transformation is what we're trying to get out of. It's a mixture, right?
I think it seems to me that they're just saying that the relative distances between all your samples in the latent space will be retained up to these transformations, affine or orthogonal.
No, well, orthogonal is easier. Affine includes everything, right? And translation.
No, of course.
So it's a mixture.
But that's what I mean. It's preserved up to linear distortions.
Yeah. But linear distortions are still significant for us to see any sources or any like.
But I think that this is not about independence. Like I think if the underlying model is something like just simple NMF, for example, non-negative matrix factorization, you could then run NMF to solve the problem after running this, solving this problem that they're showing here. Does it make sense? I think it's just more general in that sense that they're removing the nonlinear portion of the problem from the
under these assumptions.
Mm-hmm.
Yeah, this I agree with. As I stated it.
Okay, let's have a look at their experiments. They're trying to use those two matrix coefficient determination and mean correlation coefficient, which have been used on various papers. So they have 3 experiments, but I will give 2 of them. So one is on they use random data. If I remember this. So because when given this data, using this data, you have the general rating precise. You can assume how the in this conditional distribution is. And the M here means the match with all the assumptions. And so based on the R square, which is a coefficient determination. So based on the theorem, they said there's a mismatch of their assumptions will not affect a lot on this performance. But for the mean coefficient correlation, when it started coming to the normal distributions and unbounded, so in the space, it will have drops of this result. And so this is what it means. The rotated version of the lattice space are indistinguishable. Then they give have any questions on their experiments? It's the main part is like they're trying to see this, then it's with the normal distribution and matching thing there. And then they give another experiment on real data, which is called this data set. And because this data set have like 250,000 samples, and which each of them has like 10-dimensional lattice space to represent the position, rotation, and spotlight polar hue to represent as a lattice space. So they're trying to reconstruct this lattice space to do that. And the result is with the supervised result, which is just to use mean square error to do the supervised training, can get this result. And then training with unsupervised based on the different kind of distributions with match or mismatch their assumptions will get these things. And then they didn't explain why they just mentioned about the normal, like the conditional distributions in normal and in the sphere phase. So we'll have this low correlation and this is their experiments. And some conclusion of their work. So what they did is influence the objectives reveal the underlying data generative factors in a self-supervised learning, and they can effectively there's sometimes assumptions are not hold, they can still get a result. And this contrastive learning comes with the data generated precise, and they explain their utility on downstream tasks. And they do mention some future works, like they said they are based on a lot of assumptions. They may beyond not just the space on the uniform distribution, but more complex works, complex distribution. And that's all.
Do you think we can use it? Like they only show it on a simulated signal with this refined distributions and everything.
I don't think so. I'm not sure because their assumptions is too restriction.
Yeah, like how they tried. So everything is just simulated, right? They haven't tried, for example, delays as nonlinearity and things like that.
No.
It's just what was their H? What was their actually G? Which G they tried in their simulation? This G and F?
You mean in the experiments?
Yeah, in their experiments, which was the nonlinear mixture?
Oh, we have, okay, we have, oh.
Yeah, this is the mixture, right?
Yes, no, this is just show you how the lattice space looks like.
In the mixed space, this is the result, right? So
Look at the access, not the images itself.
yeah, the images are the mixture. It's how the latent space is represented in, but then.
Yes.
Yeah, this gets passed to F, and F is supposed to reconstruct angles of rotation and.
Construction to 10-dimensional vector.
Mhm. Okay. Still difficult to understand what they're exactly reconstruct. Like, how can it be useful if it is rotated? If the entire
Things from their experiments were rotated is useless. So they did mention that if the result there is terribly the bottom three lines, like the showing on the normal distribution. It's the result will drop significantly. And they did mention that there's the rotation is not solvable for them. They didn't give me some point, but didn't give point details of that. What they do for the experiment, they just gave what we can see. They didn't explain their data of that much things.
So one thing that's not clear to me is if you take the nonlinear mixture and do just linear regression, compute the R square, what kind of value would you get? Very low, very high, in between? I mean, compare just the mixture, the observed space with the latent. I guess if they have the same dimensions. Just wondering if these particular measures, especially MCC, would be high as well.
Basically, the question is the measure sensitive to what we are interested in measuring?
Mm-hmm. Because one thing that I don't like about MCCs in general is that they don't look at the cross correlations, right? So they try to do the best match possible between estimate and ground truth, and then they average out the correlations of the matched correlations, right, between ground truth and estimate, and they say nothing about the other cross correlations or cross whatever measure of similarity. And that's important for assurance that you have identified things uniquely. If you have large off-diagonal correlations, there's still some mixture left in. Then this doesn't really reflect all of that.
Yeah, it doesn't look like they're even trying to demix anything, right? As their theorems show, everything will be mixed, happily linearly mixed.
No, they're not trying to resolve any IC problem. They're trying to prove the space of the match between the ground truth space and the constructed space.
So that's why I was asking about the R squared. The R squared kind of makes sense. You're fitting kind of a linear regression between your estimate and the ground truth. And if it's a linear relationship between the two, the R-square will be super high.
No, but they're doing it up to rotation, so your solution could be 90 degrees to your ground truth, and you're getting zero correlation at all.
But you would still be able to fit one of the other components to it. You wouldn't get like a zero explained variance. You may have one or other component that are orthogonal like that, but you would, because they are just a linear transformation of one another, there would be some linear fit in a multi-variable regression. Multiple regression, sorry. You would still get an R-square high if it's just a linear relationship.
But you're trying to recover the relationship, right? Because if it's rotated...
Oh, in this case, no. They're just trying to say, well, there's a linear relationship between the true latent and what we estimated. They're trying to prove that the relationship is linear. That's my reading of it.
Yeah, I'm not sure if I follow, if I agree. Like, you can rotate your basis vectors such that all of the new basis is fully, each of the elements in the new basis is orthogonal to its previous counterpart, right? And yeah, if you're just looking at this corresponding components, they're all orthogonal. So that's, maybe I'm thinking about it wrong. Yeah, but anyways, does anyone else have questions besides Rogers or comments from your reading of the paper? What do you think? No. Yeah, Yaorong, thank you. Anyone online or Rogers, do you have more questions or discussion points before we're out of time? That's why I'm wrapping up.
This is good.
Yeah, that's very good
discussion.
Yeah, very good presentation, Yaorong. And it's dense paper. Maybe we need just better understanding of high level material. What is happening. Yeah, thank you. Okay, so the meeting for the day is over. We have team up next door starting now if you want to join.